So today the idea is to talk about how to solve linear equations. If you remember last time, what we saw is how to, like, if you have an equation which is linear, how to represent that in terms of a line. So we were working more like with the interpretation of lines visually on does that look like on the phone. Today it's more like an algebraic day where it's like, okay, so if you have the equations, how do you actually work with them, solve them to like get a particular solution? And, that is what we will discuss mostly, today. Focus on, well, I should say linear equations because that is what we're focusing. Let me find give you the sections from the book if you want to write it down. By the way, I think I may have said this, but if you read down like the sections from the book, most likely, it will have more information than the stuff I mentioned in class. So I kind of I'm picking and choosing like the most important stuff, like the book will have more details, which are okay, but like they're also not like indispensable. So I'm kind of like choosing like really the stuff that you should know from this material, which is like the stuff that is useful for other courses and for other things. The book will kind of like bombard you with extra data that sometimes it can be a bit overwhelming. So if you read it, like it's good, but it's also like, just don't worry, don't freak out if you're like, okay, but we didn't go through this in class because I kind of just selected the important information that you need to know. Okay, so let me start with an example to show you what the idea of how we're going to solve these equations. So let's say that I have the following two equations. Let's trying to solve these equations. Okay, so what is the first thing to say about solving a system of equations when you're trying to solve more than one equation at a time? So what that means is that you're trying to find a value for x and a value for y that simultaneously make both equations true or like satisfied. So what it means to solve a system like this is that when you're trying, so your objective is that you're trying to find a value for x and for y for x and for y that will make both equations true. So the first thing to kind of is important to notice is that trial and error does not work for a problem of this sort. So let me just try to kind of show you why trial and error is like a bad strategy. So like a bad strategy would be like trial and error. And then I'll kind of show you like a good idea that does work. But it's useful sometimes to see what happens if you start with like something that is not the best. So what would be trial and error, like where you literally just say, okay, what if like x equals 0? Like what happens if like you just by trial, like you just like give a value to x. So let's say what happens if you try to solve like this equation by pretending or like assuming that like x takes a particular value. So what if you give x a particular value, a specific value like x equals 0, just to make things easy. Okay, so this is why I'm calling this trial and error, because literally I'm just like guessing like without any justification like the value for x. So what is the effect of doing that? So if you say that like the equation was y equals to x plus 1, right? If you say, okay, let's pretend that x equals 0, then you get y equals 2 times 0 plus 1, right? So this is like a multiplication. So 2 times 0 is just 0, so you get 0 plus 1. So you will get that y equals 1, right? Like in the first equation. So if you give x the value 0 in the first equation, for the equation to be satisfied, you need to have y equals 1. But you know, if you go to the second equation, then you get which was 3x minus y equals 5, right? Like now, if you say that x had to be 0, you would get 3 times 0 minus y equals 5. So 3 times 0 is 0, so you get negative y equals 5. Okay. And y equals negative 5. So the issue with doing it this way is that we're getting different values for y. And the objective is to get exactly the same value for, like, if you make a choice for x, like the idea would be to find a value for y that would work in both cases. Like for example, or if you make a choice for y, the idea would be to find a value for x that work in both cases. So we want kind of like agreement on what the x and y values must be from coming from the two equations. So the issue here is that the y values do not match, okay? The problem is that you've got different y values. Is that okay? So there's nothing wrong with the equations per se. It was just like the idea of like plugging or taking x to be 0, the problem. There was nothing special about 0. I just did it kind of randomly guessing. So that is the issue with that approach. So the trial and error approach is just like a bad approach for this type of problem, because like you're so unlikely to find the correct value that works. Like this is not how you should think about the problem. What is convenient is kind of to think about it more from like the pictures, like of the perspective that comes from like actually thinking about what this equation represent. So like the right strategy is more like in terms of pictures. So let me do that. Show you that. Well, like in most of this course, like if you make a good picture, like that is a good help for what's going on. So I do like to kind of have like more like a visual interpretation of what's happening, because I feel that's kind of easier to like makes it easier to understand. So let's just think about visually what's going on. Let's take a visual perspective on the problem. And that is why we talked about last time about how these lines or how these equations look like. So the first equation, let me give different colors to them, try to match them, the colors to the ones on my notes. So let's think about the first equation, which is y equals to x plus 1. This is already in the format that I mentioned last time, which is y equals something times x plus like a number. Right? Actually, probably write it here. Like the format for us of the equations, which are linear, is y equals mx plus b. This is like the format that I like, because that's easiest to extract the information. Okay, so if you do this, So what's going on here? Like, remember, B is what you refer to as the y-intercept. That is where like the line crosses the y-axis or intersects the y-axis. So in this case, it's at 1. Okay, so here you have 0, 1. So this is going to, this is where like the line passes. And then, it's kind of like up to you, but like the idea is that like you don't have to be super specific about this. Like you have already this point, and this was called the slope, right? The fact that it is positive just means that positive slope just means that it is what you call like an increasing line, meaning that like the tilt is upward. So like if you're walking the line from left to right, you kind of are increasing your height. That is how like a positive slope looks like. So like you would get something like this. Okay, so that's roughly how this line looks like. And again, positive slope means that as you like, if you think of this as a road, if you walk along the road, then like your height is increasing as you walk on this road. Okay. And what happens with the other equation? Let me write it down here. So if you do 3x minus y equals 5, first, it is not in the format that I want, right? Because I wanted, y equals something. This is not solved for y. So like, let me solve it quickly for y. So like, just show you like the quick steps, right? So this is -1. And then if you multiply by -1 on both sides. I mean, I don't know, I did it a bit too complicated, I think, because like, but I'm just trying to do it always like so that the y is on the left side, like which is not necessary. Y could be on the right hand side of the equation. It's like the only important thing is that it should be y equals something. But like maybe doing it in this other way shows you a little bit of what these steps are like. Okay. So now, yeah, sorry.
I have a question. How does the negative sign move over to the right?
Oh, perfect, excellent. So let me do this step here again. Actually, it's good to have done it in this longer way because maybe it shows some of those things. So this is -1. Let's be more explicit. This is -1 times y, right? So what you can do is multiply by -1 on both sides because like negative, like it's kind of like this thing negative becomes positive. And so let me put it like this, -1 times -1 times y. It kind of looks a bit of an overkill, but it's kind of good to kind of write it down explicitly. And so now the -1 times -1 becomes 1. So you get 1 times y. And then here, like I kind of distributed there, once I had like these minus signs. That's how I got. Is that making sense?
Thank you.
Perfect. Okay, and now I do have the line in a format that I like. So what does this mean? The intercept is at -5. That means that this line is going to pass somewhere near this point. Again, like you don't have to do things at scale. Just like a reasonable, somewhat reasonable picture is not that enough. Let me check on my arrows here. I'm sure they will appear eventually, so they're somewhere here. I'll lose a table. Okay, this is a line also. So, and then, okay, again, like a line, there are many lines that pass through this point, all these ones that I'm showing you right now. The fact that it's, the slope is 3 for this one, is kind of, that means that it's increasing. That means that, again, you're kind of like increasing your height as you walk. And if you want to do more of a more accurate picture, the fact that this number is bigger than two, right, three is bigger than two, means that the pink line is going to be kind of more vertical. So the bigger the slope, the more vertical the line becomes. So like, it's kind of like a more vertical tilt. That is less important, like wouldn't do too much for you, but if you want to understand a bit better the picture, that is what's going on. Okay, that is more or less how this line will look like. That makes sense. Okay, and then once you draw the two lines, then you can see something more clearly, which is the two lines intersect, or they're going to meet at a point, right? So let's call this point, X comma Y. And the point, the point of this point is that being in both lines, it satisfies both equations of the lines. So essentially, when you're trying to solve a system of equations, basically what you're secretly trying to do is find the point of intersection. So solving a system of two equations is more or less the same as like finding this magical point of intersection. So that's kind of like the big idea for today. That's kind of like the only important, of all that I'm going to say, like that's the most important thing to remember. So, when you have a system, when you have two linear equations, solving them is equivalent, is the same. Solving the system is the same as determining the point of intersection. Determining Okay, so in practice, the easiest way to find this point of intersection is to, once you have both equations of the lines in the format y equals mx plus b, you just set equal the y values. That like would be the fastest route. So how do you find this point? And like there are other ways to do it, but like I'm just trying to give you like a method that would always work. So how do you find this point? So basically what you would do is like write both equations in the format y equals mx plus b and then equate the y values. So write both equations in the format y equals mx plus b and set the y values equal to one another. Um, so for example, in that case of these two lines, we already have them in the format y equals mx plus b both. So I have y equals 2x plus 1, and I also have y equals 3x minus 5. So if they are to intersect, their y values must be the same at this point of intersection, so you just kind of like take the right hand sides and set them equal to one another. That's kind of like the nice thing about writing them both in the same way. So what you set equal is the right hand side of both equations. And then you just solve for x here, like, the easiest way to solve for x here in this case is to subtract 2x on both sides. So let me do that quickly. Let me put in color what I'm doing, like the operation. So I'm going to subtract x from both sides. Okay, so that this x with this minus 2x gives me just the 1 here left. Then 3x minus 2x is 2x. And then this becomes -5. And then what you can do next is add, add 5 to both sides of the equation. Right, so put that. And perfect, like it gives you that x has to be 6. That works for me. Copy this. And once you have the x value, you can find the corresponding y value, but kind of going back to the equation. Which one your favorite? Because they're supposed to intersect it, so they should both give you like the same value for y. But it's kind of good to do it like at least once like explicitly so that you see like you get the same value for y. So if you take y equals 2x plus 1, right, and you take x to be 6, you get that y equals 2 times 6 plus 1. So this gives you what? 12 plus 1. So okay. 12 plus 1, which is 13, right? And then if you have taken the second equation, which is y equals 3x minus 5, you get y equals 3 times 2 minus 5. Oh, sorry, 3 times 6 minus 5, because like x is 6 in this case. So what does that give you? It gives you y equals 18 minus 5, which is also 13. Okay, which is what's supposed to happen, because like we essentially found it by forcing them to agree. So it would be weird if you didn't find the same value. That definitely means that you made a typo, a mistake somewhere along the line, along the process. So that means that this point of intersection for this particular, for these two particular equations is 6, 13. And this is like the only pair of x and y values for where there's agreement. Any other value for x or for y, like this, the lines will give you the different remaining values. So if x had been 5, the lines like would be giving you different values, etc., etc. So only if you choose x to be 6, then y will be 13 in both equations, or like and so on. Okay. Okay, so now you kind of do pictures, and then you think when you draw lines on a plane, what can happen? So, yeah, I think, let me see if I can find my pointers because I like that a lot. Why didn't we touch it? Mhm. Okay, fine, I knew there was some. Now, if you have two lines on the plane, what are the things that can happen? Okay, so one option is exactly the situation where the lines are not parallel. So if they're not parallel, they will meet at a point like this. The other important case that you need to know, which is what I will draw in a moment, is when the lines happen to be parallel. If the lines are parallel, they will never intersect. That's kind of like the point of being parallel. And then if you were to try to solve the system of equations, there would be no solution. So let me kind of like show you how that looks like. And how do you recognize that from the equations themselves? So let's put it here. So this is like what can happen when you have systems of equations. So what are the cases? What are the possibilities? So option one, which is the one that we just did, is that I'll just kind of draw it like this. That you have one line. And you have another line. So what is happening here is that the lines are not parallel, so there's a point of intersection. So these two lines are not parallel. Not parallel. So there is a point of intersection. So how do you recognize from the equations whether the lines are parallel or not in terms of the slope? That's a great thing about the slope, because the slope is literally, the way to think about the slope is how much the line is tilted. So for the lines to be parallel, the tilt, how tilted they are, tiltedness, like if that's a word, like it should be the same. So if one is more tilted or less tilted than the other, like they will eventually meet. So for them, the moment that these two numbers are different, they will always intersect. That's the most important thing. So if the slopes are different, the lines always intersect. There will be always a point of solution. So that's the crucial part. So if N1 and 2 are different, different slopes, the lines are not parallel, and there is always a point of intersection. Are not parallel, and there is a point of intersection. Okay. So this option is the most important case, by the way. This is usually what will happen in practice, like the lines are not parallel and then they intersect at one point. So this is the most common option. Okay, so 95% of the problems you should bet on this happening. 5% of the problems, or 4.9% of the problems, what could happen is that the lines are parallel. Okay, so option two is for the lines to be parallel, and I'll give you an example in a second. Lines are parallel. So when the lines are parallel, the slopes are the same, so like I'll just call that N for like the same slope. So the parallel lines look something like this. So what they have is the same value for M. The slope is the same, so same slope. And there won't be any point of intersection, so let me see. Intersection. So for like this is like All of these things are very easy to read. If you have the lines in this format, y equals mx plus b, things become very clear. Which is why it's important to have it in this presentation, because like, for example, like here, like, here's an example where this happens, like y. Let's say the first equation is like y equals 3x plus 1, and the second equation is y equals 3x minus 2, right? Let's say that those represent both lines. I know that they're parallel because the slopes are 3 in both cases. So this is what tells me that they're parallel. So parallel because slope is 3 for both. Okay. And so what if you don't realize that and you just try to solve the system of equations? What happens there? As I told you, when you try to solve a system of equations, you set the y values equal to one another. So you would get like 3x plus 1 equals 3x minus 2. Okay? So what happens here? Like, you can subtract 3x from both sides. And so what do you end up with? You end up with 1 equals -2, which is impossible, right? So this is never true. This can happen. And that is more or less what always occurs if you just try to force two parallel lines to be the same. Like, you will eventually get something to 0 equals 1, or 2 equals 3, or -4 equals 5. Like, whatever numbers you end up getting, like, it is what it is. But I'm just, all that I'm saying is that from the equations, like, once you have them in this format, y equals mx plus b, it will be very obvious that there's something off going on, because you will, essentially what happens is that because the x part is the same, you can always get rid of it, like, by subtracting the same amount of both sides of the equations. So you just get that b1 equals b2, but like, there are different lines, so like, that cannot occur. Okay, so like parallel lines, like, what occurs in this case is that there's just no solution. So usually, like, like, that is like a less interesting case for us, because we do want to solve systems, like, rather than just say, oh, you cannot solve it. And then you can do immediately just by recognizing the slope. So you can say, oh, same slope, no solution, basically. Is it okay? So okay, so the other thing that, just to kind of do something a little, so this is more or less how everything looks like when there are two lines involved. It's still useful to think, and I won't do more than this, but just to think what happens if there are three lines involved in system of three equations. So, because they're like something new kind of occur, and that's kind of the most that we will do, like, all these, like, there are a bunch of possibilities that you can consider, like, and if you want to kind of look at all the possibilities that you take, like, that is something like, of course, like linear algebra is actually what you spend like almost all the day doing, like, just thinking about all these cases. But so what about three lines? Three equations or three lines, right? Three equations or three lines. Okay, and also thankfully I have three of these things. So there are two things that can happen. Like, I'll kind of draw the pictures first, and I'll do an example of each in terms of equations so that we can work them out. So, like, the first option, the most likely one,
Are we gonna be having like three equations, like on our equations and stuff?
More, yes, like, like not, like, it would be like one, maybe, like, not like. I was like, twice, usually the majority will be two, but like there might be one with three, basically. Option one, and this is the most common. So the most common cases that kind of think about them as like, okay, you first have two lines, right? Let me see if I can hold them in place. You first have two lines here, and you kind of draw like a third line, and then what will happen? Let's see. Actually, I think it's better if I draw the picture because I need to extend them a little bit better for this to look the way I'm planning. So what would happen is something like this. You have this line. Have this line, so these two lines intersect at this point, right? But then you have the third one, which kind of looks like this. Okay. So what's happening here? Like the lines do intersect, but kind of like at different places, right? So like the purple and the blue one intersect here, the purple and the green one intersect here, and the green one and the blue one intersect here. So they do not agree where they're intersecting. It's kind of like three roads, like draw three roads on the city. That it is possible. You could imagine, like the roads like could intersect like at different points because like they just don't have like a common agreement. So what happens here is that you have like a point one, a point two, and a point three. Right? Where they kind of in pairs, as pairs, if you take two of these lines, there is an intersection, but there's no common intersection between the three of them. Okay, but let me put it in words here. Like, so what's happening is that they do intersect in pairs, but not the three together at the same time, if that makes sense. Intersect in pairs, but not the three of them together. And then option two, which you have to be kind of be super lucky for this to happen, which is like the three happen to go all through the same point. Like that is like less common because you kind of really need to nail things down, like, to make it work. So option two, like less common because it's really special for that to happen, is like something like, let me see, let me find it already. Something like that. Okay. So all the lines pass through exactly the same point. So all the lines intersect the pair, like the intersecting pairs, but always in the same point. So the lines. So how can you tell the difference between the two of them? So what happens is that when you have the three equations, the y values, when you kind of set them equal to one another, the y values all have to, like, for this to happen, the y values must always coincide. And for this to happen, like, I will do it in a second, but if you equate the first with the second, then you get a y value, and then if you do like the first with the third, then you get a different y value, and that tells you, okay, there's something going wrong. So the point is like, it's kind of more like, like here, there's no agreement on the y values that you will find when you start setting the equations equal to one another, whereas here, they will always agree on what's going on. So it's kind of like think about this problem as doing two of the previous problems, basically. You just want to see whether you find the same y value or different ones. So let me. Yeah, is that kind of making sense? Let me do it with a few examples. So let's do it for option one, like. So what happens with option one, if we could have something like this, we could have, usually the other way to write all the lines together is like just to like. Put them inside this like a kind of like half a parenthesis, like or like bracket of sorts, like. So this could be the first equation, the second equation can be something like this. And the third equation could be something like this. Okay, so what you want to do next is equate them in pairs. So let's call these equations like A, B, and C. Okay, so let's equate them in pairs. Equate in pairs. So let's say that A has to be equal to B because if there's like a solution, like all the y values must always agree. So you say that A has to be equal to B, then you get that 2x minus 1 to be the same as 3 x minus 2. Okay. And then what can we do? We can subtract 2x on both sides. So just do that. Well, I don't subtracted but so you get -1 equals -1. Okay, so this one gives you x minus 2. Okay. And then I'll add 2 on both sides. So I'll do -1 plus 2. 1 plus 2. Okay, and that gives you what? That gives you 1 equals x. Picture, the way I drew it, let me see what, okay, yeah, the way I drew this picture is completely off just because. The, like, if I want to do something more accurate, the intercepts have to be a little bit better, so I'll kind of redraw it. So that like it matches a bit better with the picture that the lines look like in this case. Because what I want, the blue line passes through -1. So here you have the blue line, the purple line passes through -2, so and it looks like this. And then the green line passes through 2, and it's decreasing, so maybe, this does, okay, this looks way better, so. I wanted the picture to match the equation to match the picture. So, saying like blue and purple. Blue and purple is somewhere in here. Blue purple, so x has to be 1. For the blue purple, x has to be 1. And then once you have this value for x, what would be the corresponding y value? You can put it in each of the first two equations. So you get 2 minus 1 or 3 minus 2, regardless, you get 1. So this point is 1, 1. So and then y for this value, you get y equals 1 as well. So that is how the first two set equal to one another would give you a point. So far, so good. So that is what I get from equating the first two equations. Now I can do the first with the third or the second with the third. It's actually up to you. You just have to take two of the remaining equations and equate them. So, I mean, let's do first with third, like, but again, you could have done two, second and third, and it would still work the same way. So let's say what happens if I do, so it's not like, terribly difficult, but like, you do have to be a bit more organized than like in the previous case, because in the previous case, there's only one pair to work with. There here like three pairs you can take, right? If you have a group of three people, there are three possible pairs you can take out of that. So here you have A equals C. So if you do A equals C, you get two x minus one equals negative x plus two. Okay, so I'll add x on both sides of the equation, so I'll do two x minus one plus x. And then I'll do negative x plus two plus x. Okay, and then this becomes three x minus one, and then this, like the x's will go away here because like it becomes zero, so you get two, and then let's add. Did I copy the correct ones here? Oh, okay, okay. Oh my god, like this is fine, but like this is actually the case where like they all meet. So let's keep, sorry, like, okay, so I kind of did them backwards because hey, it's like the wrong page. So this is fine, like let's just leave it like, sorry, this will be option 2. So if you can erase that. So this is actually going to be the case where like all the lines meet, which is great, but and okay, that's how you see like that this was being forced by the equations, because you get what is going to happen. You get like sorry to go back. So you get three x equals 3. And right, so what is happening here? Like you get exactly the same value for x, right? So if you get exactly the same value for x, you're going to get exactly the same value for y here again, or here, like you get negative 1 plus 2, which is 1. So, and again, y will be 1. So then, like what happened here is that the blue and the green also met at 1, 1, and so that forces that would also force the purple and the green to meet at 1, 1. So this is the case where actually all the equations match with one another. So you find the solutions from two pairs, and if they agree, then perfect. If they disagree, then that means that there won't be any solutions, and that's what I'm going to do next. Sorry, so I kind of flipped it with my desired strategy because I kind of read the wrong page from the iPad. But is it kind of making sense how it like showed up? So you just check whether like they both intersect at the same point. You could also have done BIC, and you would also have found in this case 1 and 1. Yes, good. So it's only again like you have to select two pairs. And so you can do 1 second, 1/3, 2/3, 2/3, and then just grab one of those. You could do all the pairs, but it's a little bit more than necessary, right? But the minimum that you have to do is that two of them like twice, like equal to one another. But yeah, if you want like extra verification, like you can like do purple green, and you would also find 1, 1. But like there's no other way for this to happen, because like yeah, if you think about it, if you know the blue and purple meet at 1, 1, and blue and green meet at 1, 1, like then yeah, like purple and green have to meet at 1, 1. It's what you call like transitivity in mathematics. That if A equals B and B equals C, then A equals C. Basically, it's kind of like that same idea. So there's totally fine if you want to kind of like do all the pairs, but it's a little bit more than necessary. So, but that kind of shows you like an illustration of what the idea is, like, which we won't do because it's a little bit tedious, like 4 equations. If you had 4 equations, you have to start grabbing all the possible, like, kind of like a similar strategy one with 2, and then one with 3, and then one with 4, like, you have to kind of start checking more like potential like intersections and things like that, and that's where it kind of becomes a little bit like gross, more like in size, because you have to check more possible pairs, and it's like a mess. But 3 is kind of still manageable enough, that kind of shows you a little bit of what's happening, once you have more
But
solutions.
can you go over again why after it says like one equals x, it also says y equals x, or no, y equals one?
Oh, the thing is that once you have the value for x, right? You can return to your favorite equations and plug it into the equation. So for example, if you plug it into the blue one, you get again 2 minus 1, which will give you y equals 1. Or if you plug it into the green one, you get a negative 1 plus 2, which also will give you y equals 1. So once you kind of like got the corresponding for value for x, you can always find the y value using your favorite equation. That's a good thing. Like, it doesn't matter which one you do, basically. Is that making sense?
Yeah.
Okay, perfect. So, and now option one, which is the one that I wanted to do first, is like, let's do an example where you see like they do disagree on the values. So, and that's kind of like the last thing that I wanted to tell you about for today. So let's do, let me see if I can, hopefully this picture is going to good. I'll draw the lines again um. Okay. So what option one would be something like this. Okay, so on the look here. If you were to do the picture, I can leave this, we'll see in a second, that's what happens. So the blue one passes through 0, 1, so, and it's increasing, it kind of looks like this. And the green one passes through 0, 2, and is decreasing, so it kind of looks like this. And the purple one passes through. Okay, so. Okay, this makes it very misleading because it's not necessarily true. They will be there, so let me see if I can filter it a little bit more. Yes, like we'll, like again, you don't have to do a super accurate picture, I'm just trying. And then let's do one the negative intercept, so I can kind of prepare this picture ready. So. With the things I have to extend this a lot. Sometimes these lines need to be extended a lot to see the intersection. So like, yeah, that's why something like GeoGebra is better, because you can double check that, like the picture is a bit more accurate, but like, like, in this for this type of problems, like, it's all like with the setting up the equations equal to one another, and just trying to kind of like show a bit more of what's happening in terms of the picture. But, you can like, I can show it on GeoGebra when I'm done with it. So that you see, how they actually look like if you wanted to do like a nice picture. So let's go to equation D, E, F. Mix them up with the others. So what happens if you do D equals E, D equals E, let's see, you get x plus 1 equals negative x plus 2. Okay, so I'll add an x to both sides, so x plus 1 plus x equals negative x plus 2 plus x. So now this becomes 2x plus 1, and then this becomes 2, and then I'll subtract,
Wait, what do we subtract, like, Are you switching like from left to right or right to left?
Oh, I'm going to leave the axis on the left.
Oh,
Yeah, yeah. Just because like the one on the left already had like the positive coefficient, and that's kind of nicer just to have like the positive stuff on the left. And then I subtract one. Yeah, like this picture, like is not super great. I'll show it to you in GeoGebra in a second. So I'll subtract one from both sides. Okay, perfect. And for this x value, this is blue-green. For this x value, what is the y value? Like you could take, like, again, you can use any of the equations. So if you take y equals x plus one, you would find one half plus one, which is 3/2. Okay. And so this point is supposed to be somewhere like at 1/2, comma. So this point is supposedly blue-green is somewhere here. Crazy. That is what first and second tell you. Now, for example, I can do second and third, just to do something different from like the previous one when I did where I did one and third, first and third. So so let's do like second and third just to do something slightly different. So E equals F. What happens if you do E equals F? Okay, and here to make my life easier, then yeah, I will keep the x on the right hand side because you like when I add x on both sides, then this will make the coefficient positive. So it's kind of a bit easier for yourself, like to move the x now to the right hand side, but like you eventually will get to the same answer. Otherwise. So this gives you 2. And so the idea is that this negative 1/2 x with this 1x becomes 1/2 of x. I'm just simplifying here, and then I'll add a 1/2 to both sides. By the way, always stop me if there's something like something particular sense.
wait, it's not 1.5 x? So
Uh,
if we add one positive x.
so the thing is like these like this one was negative 1/2 x. So one with negative 1/2 x becomes 1/2 of x. Yeah, if this one had been plus 1/2, then it would become 1/2 with 1, which is 3/2. If that makes sense. But yeah, like you said that this one had like a negative sign already, so that's why.
So when you add 1/2 x to x, it's gonna be.
So if I had something like this, right? Then yeah, here like I mean you can put like if you want the one explicitly, and then the numbers add, right? Which is 3/2 x. But like maybe it's better like if you put it like this. One way to think about it is kind of like because it doesn't matter in which order you put like a sum, like you can flip it so that it looks like x minus 1/2 x, just to put like this 1 second. And so here, like like the coefficient,
Oh,
it does make sense. Oops. Let me just project quickly because I didn't. Yeah, I guess someone wants to say that in the video recording. Does that make sense with everyone else? So yeah, like usually like the way to make your life easiest is always try to make the book number in front of the x positive. Like so that's why I kind of decided just to keep the x on the right hand side. But like those are more like tricks. Like so now I add 1/2 to both sides. Okay, and then 2 plus 2/2 looks like 5/2. And Okay, we're almost there, finally, and then you say multiply by 2 on both sides to, to get the x have to be. Okay, perfect. Now I do. And this is actually not such a bad picture because it's super far away, x had to be 5. Oh my god. So here's like 5 for x. I'll still put it in the rest so that you can see something nicer. That's 5 for x, and what would have been the corresponding y value? Then you plug it in your favorite, you can plug it in your favorite equation to substitute. Here, I prefer to substitute in the green one because there are no fractions and I don't like fractions, right? So it would give you the same answer, but what do you want to make your life harder? So if you put like y equals negative x plus 2, like since x is 5, you get that y equals negative 5 plus 2, and then that gives you negative 3. So yeah, it's not such a bad image, but I have done it a bit better. It would have been like not such a mess. But the only thing that I care is that this point is different from this point. Like that's more than enough to conclude that there will not be a solution to this line, to this system of equations. Does that make sense? So that's all that I care, that we found different values for x and y. Like, so even here, the fact that this is not 1/2 is more than enough to stop. You don't have to find the corresponding y value. That's enough information to know that this is not going to work, but it's still kind of like useful, I guess, to find everything out. But let me put it here, enough to say this does not work. Say there's no intersection. There is no like overall common intersection because again, in pairs they do intersect, but not like kind of with the 3 together. Okay, so let me just show you quickly in GeoGebra how that looks. And then I'll just give you some quick problems for you to work on about doing like your own line equations, intersections. But every single problem is exactly the same way, like once you have them in y equals mx plus b format, you just equal the y values, and then it's kind of like, yeah, you do have to be careful with the arithmetic, like the simplification of the equation, making sure that you don't do any mistakes because it's easy to just like overlook a sign and add things incorrectly. Like so, those are the things like they do require some precautionary stuff. So let me just show you the lines, and then I have to do it. One will look at that. So the first one was the blue one was x plus 1. So there you go. There it goes. I'll change the color to blue so that it matches the one on the board. Then the green one was y equals negative x plus 2. So I'll change this one to green. It matches the board. Also, yeah, you see here like 1, 3, where's what did it say? Yeah, 1/2, 3/2 was the point of intersection. So 1/2 is 0.5 and 3/2 is 1.5. So like this is the first point of intersection that we have found before. The last one, which was the purple one, that's minus 1/2 x minus 1/2. Oops. Okay, and then I'll do it in purple, just match the colors. And then you see like the other point like being somewhere in there, right? So in practice, like this is also why I like to show you this, because any question that I give you, you can always go to GeoGebra, enter it, and see how it looks, and that ahead of time will tell you is there an intersection or not. Like so, even just from this picture, I know this line, like the system of equations, will not be solvable because they really have to meet at the same point, and then if they're here like 3 points of intersection, So knowing like how to represent the equation visually, like kind of like makes your life easier for anticipating whether or not there's a solution to the equations. So let's do the quiz.